Hello, I'm Taeyong Jung in the School of Electrical and Electronic Engineering, taking advanced topic in social IT. Today, I'll introduce the paper Reducing Offloading Latency for Digital Twin Edge Networks in 6G. This paper was published in IEEE Transactions on Vehicular Technology in 2021. First, I'll introduce the paper's abstract and uh, proceed to present the rest of the presentation according to the outline. Recently, 6G has been envisioned to perform wireless communication and computation through digitalization and connectivity of real-world network environments. Among them, mobile edge computing, called MEC, is very complex and unpredictable in the network environment of 6G, so it is necessary to propose a new way to solve the problem of mobile offloading. Existing papers on MEC offloading mostly ignore users' mobility and unpredictable impact on the MEC environment. Therefore, in this paper, the digital twin called DT of the edge server estimates the state of the edge server, and the digital twin of the entire MEC system provides training data for offloading decisions. DT didn't propose a mobile offloading method to minimize the offloading delay under the constraint of the service migration cost accumulate while moving users. In particular, the Lyapunov optimization method used to simplify the formulation is utilized to simplify the long-term migration cost constraints for the multi-objective dynamic optimization problem. So the problem is solved by actor-critic deep reinforced learning. Through the simulation, the method proposed in this paper effectively reduced the average offloading delay, offloading failure rate, and service migration rate compared to the benchmark method, while also reducing the system cost with digital twin support. This presentation will proceed with the following outline. In recent 6G, the real network environment has been established as a digital representation to improve the wireless communication and computational performance. As mentioned earlier, especially in mobile edge computing, digital twins must be introduced to solve the offloading problems caused by the complexity and unpredictability of the 6G environment. In this paper, this paper introduced the digital twin edge network called DTN algorithm, in which the edge server's digital twin estimates the edge server states, and the digital twin of entire MEC system provides the training data for offloading decisions. Two formulas for digital twin are described with an indicator to identify the edge server in the environment. The first is the digital twin for edge servers. This formula is for understanding the computation performance of actual edge server and the estimated computation performance. The second is the digital twin for the whole system. This formula is for the reward for selecting an edge server that is different from the overall edge server condition. Moreover, this is the formula for the task information that the mobile device offloads. It consists of the size of the task to be offloaded, the total CPU cycles required, and the latency requirements. Lastly, service migration cost is incurred when the edge server of the mobile device to which the mobile device was previously connected selects another edge server. If this goes from t-1 to t, and goes to another edge server, ht minus 1 will be 1 and ht will be 0. Looking at the left first, the equation is an objective function that determines the selection of edge servers to minimize latency for the task to be performed by mobile device. Also, the formulas are shown below consist of constraints on service migration cost and latency requirements. Latency is composed mainly of latency for computation and latency for communication. Communication latency is based on propagation delay to consider the delay caused by the distance. And for the computation latency, the latency according to the task size and edge server's computation power is considered. It can be seen the formula for G, large G, to introduce the gap between the actual edge server performance and the estimated edge server performance of digital twin layer. The right formula is the performed formulation simplification for DRL based mobile offloading. Here, rather than putting service migration cost as a constraint, this paper proposes a migration cost duplicit Q based on Lyapunov formula, designed not to consider long-term constraints. The simplified formulation objective function on the previous page consists of a reward function. In addition, the state consists of the distance between the user and the edge server, the status value of the edge server in the digital twin, and the estimated deviation of the true value and estimated value of edge server, and the migration cost deficit Q. The action consists on ET that selects on edge server. In addition, the state value is composed of cumulative reward and is composed of reward decaying factor. Furthermore, the algorithm formulation for actor creating network is as follows. The first equation below relates to temporal difference called TD learning of creating networks with training. The error formula consists of state value and current reward in two adjacent time slots. In addition, the formula of critical network parameters and the actor network parameters is composed of the critic network parameter of the squared loss state value and the actor network parameter composed of the probability distribution for each action in policy-based network. If the difference between the actual and expected rewards is negative, it indicates that the action is not good. The action is bad. Therefore, the value of the output probability of WA should be set in the direction that it becomes smaller. The algorithm is composed mainly of a training algorithm and an algorithm that performs actions determined through training. In this case, the critic network's training and actor network are sequentially performed. The training of the actor network is also performed based on the training made in critic network, and each parameter is optimized and saved. Therefore, the algorithm on the right determines the action based on the corresponding parameter, uh, and this indicates the online characteristic of moving on the next state. And this algorithm returns edge server, which is selected by uh, moving user. When looking at the number of edge servers based on the proposed algorithm, the estimated deviation of edge server performance and the upper limit of the migration rate, the proposed algorithm showed better performance than the benchmark in average latency, task failure rate, and system cost. It indicates that it is showing. In particular, other performance are also low, while the system cost shown at the end is minimized. Uh, let's look at the fourth graph. As the movement speed increases in the service migration rate, it can seem that the upper limit of migration rate is lower than the benchmark in an environment where it is low. This can be seen as a phenomenon caused by reducing migration effects to maintain the low service migration cost. So in a high movement speed, the benchmark's performance is better than the proposed scheme when the beta is 0.2. Uh, in conclusion, this paper developed a digital twin edge network called D10 architecture for 6G in the mobile edge computing environment. D10 was formulated to minimize uploading latency under the constraint of cumulative migration cost. In addition, a simplified formulation based on Lyapunov was formulated to minimize uploading latency under the constraint of cumulative migration cost. In addition, that proposed simplified formulation based on Lyapunov dynamic was solved with deep reinforcement learning called actor critic algorithm network. This actor critic network algorithm has been shown to effectively low average latency and task failure or the migration rate based on uh, low system cost relatively. Thank you for listening, and this is the end of the presentation. Thank you.